Hey everybody, welcome back. My name is Eric Scheidel, the HVAC Service Mentor. Still. Hey, I'm glad to be with you, especially in this unique time. Hope you're all hanging in there and doing well. Today's topic of conversation is going to be about troubleshooting electronic circuit boards. These days, pretty much everything that does anything is going to be equipped with an electronic circuit board. And that hasn't always been the case. You know, I'm old enough to remember back when furnaces didn't have electronic circuit boards. When I started in my trade, I was still working on things that had been installed back in the 1960s and 70s even. And of course, those didn't have a whisper of electronics in them. Everything was electromechanical. Today, electronics have taken over our industry and pretty much every other industry as well. Now, as ubiquitous as they are, electronic circuit boards still provide or produce a great amount of confusion, and that confusion results in a great amount of misdiagnosis, meaning electronic circuit boards get replaced when they're not bad. That's the main problem that we have with troubleshooting circuit boards, is we identify there's a problem with the board when there actually isn't one. And to illustrate this point, many years ago, I was talking with a representative from Linux, and he shared with me that a significant amount of the electronic circuit boards, and other parts too, but mainly circuit boards he was talking about, that they receive back under warranty, they'll test them, and they find that there's no defect with them, none at all. Fast forward about 20 years into the future from that conversation, and I had another conversation with a manager for York. And this was actually at the York factory in Norman, Oklahoma. And I asked him about the same thing. And he said, for us, it's closer. We are seeing 75 to 80% of all of the electronics that they receive back under warranty have no defect with them. And what that tells us is that just really illustrates that there's a lot of confusion around electronic circuit boards. And the way this manifests a lot of the time is people will tend to just throw up their hands and go, something is wrong. I don't know what it is. It must be the circuit board because, well, they just stop right there. It must be the circuit board, period. And they replace it. And lo and behold, still has the same problem. One of the reasons I think why people jump to this conclusion is because the control board is in control. It covers all of the operations that go on in the machine that you're working on, or a significant amount of them, and it's the most mysterious and complicated part. Therefore, it must be the problem. Not so fast. Let us get into what we're going to talk about today: troubleshooting electronic circuit boards. And I think it pays to mention right off the bat that what I'm going to teach you today is going to be an overall strategy on how to approach and how to troubleshoot any electronic circuit board in any kind of a piece of equipment, no matter what it is. Now, these things are so varied, they differ a lot depending on what they're being used for, depending on what equipment they're in, depending on what brand they are. I mean, there are so many varieties out there. It is really impossible for anyone to give you a step-by-step guide for anything other than one specific board, and then another specific guide for another specific board. And that is honestly way too much information for anyone to just keep in their head or be able to utilize. Instead, this is going along also with our troubleshooting series. I'm going to teach you some logical steps that you can take in every situation that are going to lead you closer to success in troubleshooting a piece of equipment that has electronic circuit boards in it, specifically down to the board level. Now, before we move on, I want to say what I mean by the board level. Let's take a look at our title slide here. Here's our little furnace control board in a gas furnace. We are not going to be replacing components on circuit boards. That is really kind of a big no-no. There are those in the industry who will promote doing that. However, I am not one of them. I am going to say that if there is anything wrong with your electronic circuit board, you do not replace any components on the board, you simply replace the entire thing. The control board is a discrete component in and of itself, and it is replaced in its entirety. Do not replace components on the circuit board for many reasons, but it is asking for trouble in all cases. And another more specific reason why is, say you've identified, if you're an electronics genius and you're able to identify that a specific component on the control board has failed, and you're going to replace it. Much of the time, the reasons for control board failure aren't because this particular component had a problem. It is often more because the entire control board or the entire circuit that component is in has experienced a problem. And all of the other components that are in that circuit or a part of that control board have experienced the same problem, which means they could be weak or show hidden damage, and it just doesn't make sense to only replace one component. We replace the whole thing. Okay, moving on. In order to understand the idea behind electronic circuit boards, it's important to understand where they come from. Electronic circuit board controls have evolved from manual controls. Manual controls like physically adjusting the damper on a coal-fired stove, for example, to control the heat, right? Then they moved to mechanical controls, where the human element was taken away and something would respond to the temperature and then automatically manipulate that same type of damper. That moved into electromechanical controls. Electromechanical means that there is an electrical component and a mechanical component. A mechanical component is something that physically moves, and an electrical component, of course, is electrical. So something is physically going to move and then trigger a switch. An example of electromechanical would be a conventional thermostat with a mercury bulb, right? The mechanical part is the part that moves, the thing rocks back and forth. We have a temperature sensitive element that physically moves in response to changes in temperature, and that movement activates an electrical switch. That's what we mean by electromechanical. And the reason why this evolution happened is multiple reasons why. It gives us greater control accuracy, number one. It allows for more independent automation, for two. And for three, it allowed the safe use of liquid and gas fuels. Now, I'm fortunate my father was involved in operating a coal-fired boiler plant when he was much younger, before I was born, when he was in his late teens, early 20s. That was his job. And the coal-fired boiler plant that he worked on had been originally built around the late 1800s and was still serving the plant that he worked in. And so he had a lot of this experience with these manual and strictly mechanical type controls. And I was able to apply that into what I do and be able to kind of observe in a roundabout way this evolution from manual to mechanical to electromechanical and now to electronic. But in those earlier days of mechanical and manual, it really required a boiler operator to sit and babysit the thing and operate it 24 hours a day, 7 days a week. And that was what my dad's job was. Well, the evolution of controls is allowing that level of human oversight to go away, more automatic. It's really helpful for us to remember that electronic circuit boards are there to essentially do what has always been done before. Imagine our gas furnace, for example. Our gas furnace, what is it supposed to do? It's supposed to turn a burner flame on at the right temperature, turn it off at the right temperature. It's supposed to turn a fan on at the right time and turn it off at the right time. And that all used to be done by mechanical and electromechanical controls. And now it's done by electronic controls. It's doing the same thing, only, more independently, more automatically, more accurately, and also more safely. I want to illustrate that real quick here. Let me get my pointer in the right place. There we are. Check this out. This, as you can tell, has an electronic circuit board built into it. Here's the back side. There it is. You might think, what in the heck is this thing? This is pretty unusual. This is a contactor. This does the exact same thing that a conventional contactor in an air conditioner or heat pump outdoor unit does, right? On demand, it closes a set of contacts, which energizes a compressor and a condensing fan motor. That's what it does. As you can see, it is significantly more complicated than a standard contactor. Essentially, it does the same job, but it does a few other things as well. It has some built-in time delay features to prevent short cycling of that compressor. It has a built-in brownout protection, so it monitors incoming line voltage, and if the line voltage is inappropriate, it won't allow the compressor to try to start. It has some other safety features in it as well, which help protect the compressor. This is essentially what it does. So here we have a contactor that does everything an old contactor used to do with some enhanced additional features that end up being actually really valuable. This is called an Emerson Sure Switch, if you haven't heard of it before. It's made by Emerson Climate Technologies. They, as far as I know, have not appeared in OEM equipment. This is an aftermarket part that you can use to add value to your service and install on existing units. And they have some other really cool benefits as well. But I just wanted to use that as an illustration to show that electronic control boards essentially do the same thing that they've always done, control-wise, with some additional enhanced features, and to go along with that is some additional complexity. There we go. There's my pointer. So where are we going to find electronic circuit board controls? They're everywhere. There's gas ignition control modules where all they do is they fire up a burner. Blower control boards, which operate blowers, obviously. Integrated furnace controls, integrated rooftop unit controls or packaged unit controls. Electronic thermostats. Hey, that's a circuit board. It sure is. These are some of the most common ones that you'll find out in the field. Most commonly will be the integrated furnace controls. And now as we get into more and more sophistication and more desire to control the, how do I say this? The load matching of our gas and air conditioning equipment. What do I mean by load matching? Well, let's think of air conditioning. When it's the hottest day of the year and the air conditioner runs, it is producing its maximum performance and it also achieves its maximum energy efficiency. Whenever it's not the hottest day of the year, it's something less than the hottest day of the year, but still warm enough to require the use of an air conditioner, we call that part load. Okay? The hottest day of the year, that's full load. Anytime else is part load. And under part load conditions, the energy efficiency of the air conditioning machine is less than what it is at part load. Because our equipment operates at part load almost all the time, and it operates at full load very infrequently, it makes a lot of sense for us to vary the capacity of our air conditioner to match the demand. And so doing, maintain the energy efficiency of the unit. And that level of control requires some very sophisticated operations controlled by electronic control boards. In one of our slides down the road, we're going to see a unit that does exactly that. Another great example of that is inverter drive mini split air conditioners. They do that, and they have a ton of electronics in them to make that happen. Some other types of controllers we'll find are heat pump defrost controllers, hydronic zone controllers if you do any boiler work, delay timers. They're very, very common in condensing units. Communicating controls. a whole different animal. We'll talk a little bit about communicating controls. Economizer controls on light commercial package rooftop units, and lots of other things. They are literally everywhere. They're in your toaster, or at least your toaster oven. So in order to help kind of wade through all of these different things, I've developed what I like to call the control board or circuit board unified field theory. And if you've been around any of my classes for very long, you know that I am all about the big idea. What is the big idea behind this? What's the main concept? Because if you can understand the main idea, it allows you to understand the details very, very well. And this is where I see a lot of technicians leading into misdiagnoses on electronic control boards. It's because they get too bogged down in the details and they forget the big main idea. If you can remember the big main idea, boy, it's going to go a long ways toward helping you ensure your success. So here's what it is. The purpose of every circuit board is this. It is to energize and de-energize specific loads in a specific sequence based on specific inputs and internal programming. The purpose of every circuit board is to energize and de-energize specific loads in a specific sequence based on specific inputs and internal programming. And because of this, you can think of all electronic circuit boards as a relay on steroids. And to help prove that point, what we have down here at the bottom of this page is what is known as a smart relay, also known as a programmable logic controller, or a PLC. Smart relay. And that's really what it is. It's a relay on steroids. And every electronic circuit board in all of our HVAC equipment can be considered as such a thing. So this sentence right here really kind of drives home what the things that we need to look at when we are doing any troubleshooting on an electronic circuit board. And that is energizing and de-energizing specific loads, the sequence, the inputs, and the programming. That's what we're going to be paying attention to. Okay, let's do that. So regarding our main idea, the first thing that we need to know is what in the heck is this control board supposed to do? What is its job? And simply by looking at a control board, it's not always obvious what it's supposed to do. It just looks like a whole bunch of wires and electrical components. So let's investigate a little further. And let's start with the loads, because remember, every electronic circuit board's job is to energize and de-energize specific loads. So if we can figure out what loads it energizes, that's going to give us a long way down the road to identifying what it's supposed to do. So for example, a integrated furnace control board is supposed to energize a gas valve. It's supposed to energize a draft inducer motor. It's supposed to energize a blower motor. And it's supposed to energize an igniter. Cool. That simplifies things quite a bit. Not only is it supposed to energize these things, it's also supposed to de-energize them at the right time. And this leads us into the sequence of operations. When you have a piece of equipment that is controlled by an electronic control board, the electronic control board is programmed with a sequence of operations. And the better you know what that sequence of operations is supposed to be, the better you're able to analyze how that control board is functioning, what it's supposed to do. Remember, the job of the electronic circuit board is to energize and de-energize specific loads in a specific sequence based on inputs and internal programming. So that sequence is based on its internal programming. And how do you know what the sequence is supposed to be? Well, that can be challenging. You will find it in a combination of the schematic diagram for the unit and the installation and operations manual, also known as the IOM. Every IOM for every piece of equipment has a section called Sequence of Operations. And if you read the sequence of operations, what you are reading is the step-by-step operation sequence of that electronic circuit board. Once you've identified that, or if you at least have a pretty darn good idea, for example, if it's a gas furnace, it works the same way most gas furnaces do, you have a pretty good idea what that sequence is supposed to be. The next questions you need to ask yourself and then answer are, what are the things that tell that electronic circuit board to work? How does it know to do its thing and when? For the example of a gas furnace with an integrated control board, the thing that tells it what to do is the thermostat. And how exactly does it do that? What are the inputs that the thermostat gives to the control board? Well, it gives it 24 volts AC on the W terminal. That is an input, that is an operating command. So that's how we want to think about things. We know, what is this thing, what are the loads that it energizes? What is the sequence of operations? And what tells the thing to do it? The next thing that we're going to do is compare what the control board is actually doing is compared to what it is supposed to do. So once we've identified that the board is in fact getting an input operational command, is it giving the correct outputs? So now we need to look and see what loads are or are not being energized. Where does the sequence of operations stop? So for example, this goes right along with our troubleshooting ideas, and we identify where the sequence of operations stops, and that's where we begin our actual troubleshooting process. Remember that the sequence of operations is not all go time. It's not all go. Sometimes the sequence of operations says stop. And that could be an example of something is going on that means it's not safe to operate right now, and the control board could be responding to that, whatever that is. And that is why so many electronic circuit boards get replaced when there's nothing wrong with them. What is discovered later is that either they were never getting the input, the operating command, or there was an external situation that it was responding to saying, hey, it's not safe to run right now, I'm not going to, or I'm not able to for some reason. And that is going to mean that we're not only troubleshooting the circuit board, we're troubleshooting the holistic machine, which is controlled by this circuit board. And that brings us right into our troubleshooting process. We develop a theory, develop a reason why the theory is logical, develop a test to prove the theory true or false, also develop a reason why that test is a good idea. We perform the test and we analyze the results, and boom, there we go. Now, a lot of control boards are going to provide diagnostic feedback. And the diagnostic feedback could be in the form of a flashing indicator light. It could be in the form of a code. It could be in the form of an LCD display that tells you things. And one of the most important things to realize about diagnostic feedback is that it's not perfect. It can't account for every possible situation. It doesn't necessarily know that a plastic bag has been sucked up onto the intake pipe. All it knows is that the pressure switch isn't closing. And that's what it's going to tell you. It's going to say, hey, the pressure switch isn't closing. It's up to you to go and find the plastic bag. So not only do we need to look at the diagnostic feedback and understand it, we also need to verify that it is in fact true. In the event of a control board failure, one of the failure modes can be that it is giving false diagnostic information. For example, that pressure switch could very well be closing, but the control board for some reason is unable to recognize that because of its failure, and it's going to tell you that it's not closing. So in the event that we have a pressure switch issue, we need to verify, yes, in fact, the pressure switch is or is not closing before we do anything else. So in the event that you have diagnostic feedback, always confirm that that's actually happening before you do anything else. So that would be a new starting point. And that modifies our troubleshooting process just a little bit, because I have told you before that you begin your troubleshooting with usually a voltage test at a load or a terminal endpoint. Well, in the case of, say, hey, I'm getting a pressure switch fault or a limit fault or something like that, you need to start there and verify whether or not that fault actually exists. And that can help speed up troubleshooting very quickly. So, once we have identified that, yes, in fact, the fault code is happening, or there is a fault, the next thing we need to figure out is the control board getting everything that it needs in order to do what it's supposed to do? So, hey, imagine this example. We have a control board and it's not doing something. We've identified that it's not doing X. Say it's not energizing the draft inducer, or it's not energizing the blower, or it's not doing something. The next question we need to ask and answer is the board getting everything that it needs in order to do what it's supposed to do? Beginning with the power supply. We want to identify what is the power supply for the control board, where does it come from, and what voltage is it? And then following up with, is it there where it's supposed to be or not? I had a situation many years ago when I was in charge of a service department, and I had multiple junior technicians working under me. And one technician in particular had come from the construction side of the business, and he was not very well experienced in troubleshooting operating pieces of equipment. Had a lot of experience making and hanging duct systems, cutting holes in walls, moving equipment, installing it, running gas line, things like that. Not so much experience in troubleshooting. And he had called me up on the phone and was saying, hey, I think I've got a bad control board here. I said, okay, great. How do you know it's bad? What do you think is wrong with it? Because we're working together on this. And he says, well, I've got voltage at the control board, but it's not working. Cool. What voltage do you have? And he said, I have 120 volts. I said, great. However, that's not the voltage that makes the board work. The board runs on 24 volts. So that is important. You need to know what voltage does the board work on. Because most circuit boards, well, I shouldn't say most anymore. Maybe it is most still. Most electronic circuit boards in residential furnaces, for example, are going to have more than one voltage landed on them. They're going to have the high voltage and the low voltage. Same thing is true for smaller, like residential style packaged units that have a furnace and AC in one complete box. They're going to have multiple voltages landed on a control board, sometimes as many as 3 different voltages. So you need to know which one of those voltages is the one that powers your control board, because it's not going to be all of them. Next, is a board getting all of the inputs that it needs to operate, such as a command to operate, something that tells it go. Most of our control boards are powered up all the time, and it's waiting for that go signal to come. So is it getting it, or is it not? What is it, and where does it come to? If it's a communicating control board, is it receiving the right communication from its cooperative controller? Any safety switches, such as limit controls, end switches, pressure switch controls, refrigerant pressure controls, temperature switches, all of these things are types of inputs. And then also sensors. Some control boards are going to have temperature sensors, analog sensors attached to them that aren't just an open and closed switch. So are the switches, the sensors there? Are they operating correctly? Are they giving the right information to the board? These are all things that affect how a control board works. And then we're going to also move on to things called switchable voltage inputs and common and neutral pass-throughs. So we'll look into what all of these things are here and how to check them in our next few minutes. There we are. Switchable inputs, common and neutral pass-throughs. So, common features of circuit boards. Let's start with power supply. Most electronic circuit boards are powered continuously by 24 volts AC. If you're looking at a gas furnace and your gas furnace has an IFC, also known as an integrated furnace control, let me talk about what IFC actually means right now. Integrated furnace control is the control that operates every aspect of the furnace's operation. It controls ignition, it controls fans, it controls, it monitors safeties. It is the common landing point for all of the wires in the furnace. It is completely integrated into the operation of the unit, and it controls the entire furnace, hence its name, Integrated Furnace Control, or IFC. IFCs are powered at all times by 24 volts AC. And so are simple blower control boards. They are also powered continuously by 24 volts AC. Almost all control boards are powered by 24 volts AC in residential heating and cooling equipment. If you move on beyond residential heating equipment, you may start to find controls that have multiple power input voltages that they can run on. There are controls out there that will run on anything between like 18 volts up to 240 volts and anywhere in between. As long as you put some kind of power there, they're going to work. Those are becoming more common. However, residentially, pretty much everything is straight up 24 volts AC. Even if there's 240 volts or 120 volts landed on the board, that's probably not the power source. 24 volts AC is what powers them. Some circuit boards are only powered on demand. And that demand could be things of those nature are like ignition controllers. Honeywell S86 series control boards is a great example. Delay timers. Delay timers will be found on condensing units, or they'll be found on certain boilers for pump operation. So you need to identify what voltage is your power supply, where does it land, and where does it come from. If the board is not receiving power, it's not going to work no matter what. And it is entirely possible for the board to be getting an input command, but the board not to be powered up. Therefore, it won't work in spite of its receiving an input command. Other boards like ignition controls, the input command is the power up as well. So that is something that you need to identify, and it's not always going to be obvious. So that is going to take a little bit of investigation on your part. Next, we're going to look at inputs. So there are two major types of inputs. The first kind is called a digital input, also known as a binary input. These are two names for the same thing. Digital or binary means there can only be one of two states present. It can be on or it can be off. A switch can be either open or it can be closed. You hear about binary with ones and zeros, and in that case, the term on corresponds to closed for a switch, and that means a 1. Or off / open, I didn't realize that's a typo. Everybody cross that off and put open right there. Open equals 0. And that's why modern on-off switches on most of our electronics these days have that little circle with a little line, a vertical line in it, I and O. That's my on-off, I-O. I for on, O for off. I for closed, O for open. Switches. So that's where that comes from. In the digital or binary type of input, there's 3 major types. The first type is probably the most common. It's called a single voltage input. So a single voltage input could be the 24 volt demand for heat on the W1 terminal of your furnace control board. That's your call for heat. For cooling, that would be 24 volts on the Y terminal. Okay, that's a single voltage input. Single voltage means there's one voltage it can be. It's either 24 volts or it's 0 volts. It's not in this kind of in-between varying type of throttling thing. No, it's either this or it's that. That's what we mean by binary. That's what we mean by digital. It's either open or closed. It's 24 volts or 0 volts. There's no in-between. A demand for fan on would be 24 volts at G. That's a single voltage input. Another type of input is called a send and return. In this case, the control board sends 24 volts out through a safety switch or a control switch of some kind and looks to receive the voltage back. Voltage send and returns happen somewhere in the middle of the sequence of operations, okay? So the single voltage input begins the sequence of operations. That's your command, okay, hey, start doing your thing. And as it begins to do its thing, it's going to have one or more send and return sequences where it's going to send 24 volts out from the board, usually coming out of a wire on a Molex plug, going through a limit switch or a series of limit switches or a pressure switch, and then coming back to the control board. And the control board is going to wait to see that voltage come back before it can operate. Examples include pressure switches, limit switches, flow switches, end switches, things like that. And the third type of binary switching is called dry contact monitoring. Now, in residential operations, so far, there's not a whole lot of dry contact monitoring going on, but it's beginning to enter. The technology is beginning to enter the industry. And I predict that within the next 3 to 5 years, we're going to be seeing a lot more dry contact monitoring happening in residential equipment. It happens all the time in commercial equipment, and the technology tends to filter down into residential. What dry contact monitoring means is that the control board observes the position of a set of switch contacts. Now, on the wires and going through the switch contacts, there may be AC voltage, there may be DC voltage, or there may be no measurable voltage at all carried through the switch. Either way, there is very little or very little or no current carried through the switch, and no loads are directly energized through that switch. That's what we mean by dry contact monitoring. And so all it's looking for is to see, is the switch, is it open or is the switch closed? The switch isn't actually powering anything up. It's just providing reference information to the control board. So those are the three kinds of digital or binary inputs that we're working with. Another type of input, the second major type, is called an analog input. Analog inputs are continuously variable in nature. Earlier, when I was talking about the digital binary inputs, I was saying it's either this or that, no in between. Analog inputs are exactly the opposite. There is all in between. It isn't either all or nothing with an analog input. It's always going to be a variable input. The control board is going to monitor these inputs and make controlled decisions based on what those inputs are. Some examples of analog inputs are things like a temperature sensor, which is also known as a thermistor. Sometimes it's a thermocouple temperature sensor. A position feedback potentiometer, which is going to identify what position a movable damper or valve is in. And it's going to send that position feedback back to the main controller, and the controller is going to make decisions based on that feedback information. A Hall effect sensor. What a Hall effect sensor is a special type of sensor that identifies rotation. And the most common application for Hall effect sensors in HVAC is on commercial rooftop unit draft inducers, to identify, is the draft inducer spinning, and is it spinning at the right speed. There are potentially other uses for Hall effect sensors monitoring blower speeds and compressor speeds in variable capacity equipment as well. Again, here this is something that is somewhat rare today, but it is on its way to the residential market as we speak. A pressure transmitter. Pressure transmitters are found in modulating gas furnaces instead of a pressure switch or in addition to a pressure switch. Pressure switches will simply open or close based on a pressure set point value. So if the set point value exceeds, or if the pressure value exceeds the set point value, the switch will close. Well, a pressure transmitter will actually transmit information about exactly what the pressure is. And the pressure transmitter will sense the pressure, and it will send out a proportional signal describing what the pressure value actually is. For humidity sensors, 4 to 20 milliamp loops, microamp flame signal. That is an example of an analog input. Okay. Frequently, in the cases of temperature sensors, multiple temperature sensors will often share a common terminal. So, for example, if we have a residential zoning control system, you may have an outdoor air temperature sensor, a supply air temperature sensor, and a return air temperature sensor. And there will be a total of 4 terminals that these will land on. There will be the OA terminal, the SA terminal, the RA terminal, and the C terminal. Proportional controls often feature analog sensors and inputs. And so what a proportional control is there is, again, load matching. The output of the heat is going to match the load conditions at the time. The output of the cooling or the compressor is going to match the load conditions at the time. That's proportional control. In the event that you have an analog input, typically temperature or pressure sensor, it is important to be able to either simulate a correct input to elicit a predictable response, or to know the values of the sensor in order to test that sensor and determine if it is behaving properly. So say, for example, you have something that is not controlling to the right temperature and is using a temperature sensor. You need to know how that sensor is supposed to work, which means you're going to have to do some research. It's not going to be printed anywhere on the equipment or anywhere on the sensor. It may be in the IOM, or it may be in some other specification that you're going to have to hunt for. You may have to call up tech support to get it. And this is for a thermistor. A thermistor will change its resistance based on the temperature that it's exposed to. So, for example, here is a specific temperature sensor from a Johnson Controls A350 controller, which is a remote type thermostat, and the sensor is an A99B that's connected to it. So for that sensor, say if it's experiencing 120 degrees Fahrenheit, it should be outputting a resistance, or experiencing a resistance, of somewhere between 1100 and 1300 ohms, or maybe around 1200, 1250. So what I would want to do is measure the temperature that it's experiencing and then measure its resistance to determine if the sensor is working correctly. Sensor failures are more common than control board failures are. However, a lot of control boards get replaced when there's actually a sensor failure. Some people just go ahead and replace everything. Solves the problem, but not the most efficient way of doing it. Another input, like we talked about, is the switchable voltage supply, also known as a pass-through. Switchable voltage supplies are external voltage and current sources that are landed on the board for the purpose of being delivered to a load. For example, this is a hot surface ignition controller. It's powered by 24 volts, but it has 120 volt hot and it has 120 volt neutral landed on it. These are there because the job of this controller is to send 120 volts to the igniter. The igniter runs on 120 volts. So that's why it needs to have 120 volts coming into it, so that it can send 120 volts out to the igniter at the right time. Now here's the rub. If for some reason the 120 volts is not present on this control board, the control board is going to operate just fine. It's going to receive 24 volts on demand. It's going to close the switch contacts between the L1 terminal and the HS1 terminal, but nothing's going to happen because the voltage isn't actually there. So we need to identify in a case like that A, we have a switchable voltage supply or a pass-through, but it's not there. Therefore, the control board isn't going to be able to energize that load. It has to have the voltage coming in order to send the voltage out. So that's another thing that we need to identify and test for. Now, when it comes to communication is a little different, right? The USB cable or the Ethernet cable that plugs into your computer that sends data back and forth, that's communication. When I have something that is just a switch opening and closes, that's not communication. When I have an analog sensor, that's not communication. Communication is a send and return. It's literally talking back and forth between two control boards in a specific control language. Communicating devices cannot be normally measured or analyzed without specialized test equipment. And on the residential side, that specialized test equipment probably doesn't even exist. We're getting there, but we're not there yet. These communicating devices, they send and receive data packets back and forth using a special language. And when you're dealing with communicating systems, it's often possible to operate the device as a standalone system or as a communicating system. All of our communicating residential equipment has this ability. You can either install a communicating controller to run it, or you can install a conventional thermostat to run it. This is a great thing to know in your back pocket, because when you're dealing with communicating systems, how do you know, is it communicating? And if it is communicating, where's the problem? Is the problem in the communication being inappropriate, or is their control board inappropriate? And if it's a control board, which one? It's really hard to figure that out. So if we take the communicating aspect away and we operate it as a standalone non-communicating equipment by connecting it to a conventional thermostat, and if it works correctly, now we can start to narrow down if it's a communication issue or not. Is it the user interface on the wall, or is it the board in the furnace, or what the heck is it? So being able to switch it from communicating to non-communicating is a big help in moving to diagnostics. Another thing you should know about communicating systems is that they can sometimes be subject to interference from outside signals, and they require sometimes special wiring techniques and a special cable to prevent outside influence. If it's a system that requires that and it got installed with normal brown thermostat wire, that could be part of the problem. And so I look to see, it's going to be in the installation manual, whether or not your unit needed special cable and whether or not it's there. And if it's not there, get it there first, and then maybe all of your communication problems will go away. This is an example of a sophisticated controller from Carrier for our rooftop unit that can be either communicating through a number of different language protocols, or it can operate all by itself. So one of the things that we'll do in commercial world is, okay, I don't know if you're able to talk to the network properly or not. Therefore, I'm going to take you off the network and see if you operate all by yourself. And if you do, then I know that you're having a network communication issue, and I'll look there. If you don't, then I know that you, in fact, are faulty, and I'm going to replace you, and then your new replacement should be able to communicate to the network and operate just fine. Let's look into outputs. Most circuit board outputs will send voltage out to energize a load. And the source of this voltage is usually a switchable voltage input, which we've already talked about. Outputs will energize relays, they'll energize contactors, they'll energize igniters, they'll energize fan motors, they'll energize valves, dampers, etc. Other forms of outputs include analog outputs, such as a variable AC or DC signal, a digital pulse width modulating signal, and we're seeing more pulse width modulating on variable speed blowers and compressors, more and more common. High voltage sparks and flame sensor circuits, these are analog outputs. Now, everything that I've said up to this point sounds really confusing, I know, but it's not. If it is confusing, go back over these notes again and look to see on the circuit board you're looking at, what are my inputs? What are my outputs? What is my power supply? Do I have any pass-through voltages? And almost all of the circuit boards you're going to work on are going to have these things. But here is where you can kind of take heart, okay? The more complicated your control is, the more sophisticated the diagnostic feedback is going to be. Most of our modern control boards are going to give you some type of fault detection and operational feedback capability. The more complicated they are, the more difficult it is to measure its operation, the more comprehensive the feedback usually is. Here's an example. This is a very sophisticated, right here in the middle, very sophisticated modulating variable capacity heat pump or air conditioner, and it has an actual touch screen controller in it. It measures refrigerant pressures. It gives all kinds of diagnostic feedback. This whole thing is just a mass of electronic controls, and you have absolutely no way of working on it without this user interface. Same thing over here on this older, sophisticated Linux communicating control. This thing is required for diagnostic feedback. And in commercial world, we have a similar thing where we can have an actual plug-in thing for this carrier system that's going to give us all kinds of diagnostic feedback information. So don't lose hope. The more sophisticated things are, the more sophisticated your diagnostic feedback is going to be, and that can just make troubleshooting sometimes easier. Here we are. Let's take a quick look at an integrated furnace control. Here we have one. What is the main idea? We're going to take all these big things that I just have and just kind of apply them to this integrated furnace control. What is the big idea? What are the loads it controls? Well, it controls a draft blower. It controls the circuit blowers. It controls the ignition sequence completely. It is also going to monitor safeties and provide a safety shutdown response. It's going to be a central junction point, and it's going to provide operating and fault condition feedback, such as LEDs or a digital readout. So check this out. The blowers, those are outputs, right? Igniter, that's an output. Gas valve, that's an output. So for all those outputs, there has to be a voltage supply, right? So if it's a 120 volt blower, there has to be 120 volts coming in. Is it there? Ignition sequence, igniter, there's got to be 120 volts coming in. Is it there? Junction point, pretty obvious. Gas valve, that's 24 volts. There's got to be 24 volts coming in. Monitor safeties and provide safety shutdown response. Those are going to be our voltage send and voltage return, digital binary inputs. There may also be, in the case of a modulating furnace, there may be a draft pressure transmitter that is sending a value. And then that value is going to be used to control the speed of the draft inducer. When we are trying to sort through and identify how our control board works and what it controls, the schematic diagram is super, super helpful. Let me get my face out of the way here, and I'm going to point out to you that there is more than one diagram here. There's two, but they're both diagrams showing the same thing. The one that is on the left is what's called a pictorial diagram. The pictorial diagram really shows all of the wire connections, and it shows the components in a more graphical format. This gray square board represents the control board, printed circuit board, as it says right there. Printed circuit board, as it says right there. And over here on the right is what's called a ladder diagram. This is the exact same circuit, but it's shown in a more logical form. It doesn't show you the exact connections and the exact components. It shows you more the logical sequence of operation. And here again, the gray box is the printed control board. So I'm going to focus strictly on the ladder diagram because it's a lot easier to identify where our components are. And wherever we look at a ladder diagram, we look at the transformer first. That's the first thing we want to find because we do have two voltages, and there it is right in the middle where it should be. The next thing we need to find is the power supply. The power supply, main power coming in, is right up here at the top of the diagram. So on a ladder diagram, this tells me that everything between the transformer and the power supply is high voltage. It's all 115 volts AC. So everything up here is 115 volts. Below the transformer is everything down here is 24 volts. So first of all, what are the loads that this control board controls? Beginning with our high voltage loads, we've got this one. This is our blower motor. We've got this one here. This is our hot surface igniter. And we've got this one here, which is our induced draft motor. There they are. Controls three things. That simplifies things, doesn't it? And on the low voltage side, what are our low voltage loads? There's only one. There's a gas valve. Okay, so that's what it controls. Next, let's look at our power supply. Yes, we have 120 volts landing on the control board at these two terminals here, but that's not what powers the board. The board is powered by 24 volts landing on the SEC1 and the SEC2 terminals. That's what powers the control board right there. Next, it goes through a fuse. Then the control board leaves, the 24 volts leaves the board, goes through a flame rollout switch, goes through a limit switch, comes back to the board, and lands on the R terminal. This is the first example we have of a voltage send and return right here. Boom, voltage send, 24 volts out, through the limit switches, which are normally closed. Voltage return, 24 volts back. And you see that little dot right there? See how that takes off of that voltage and comes back to the central processing unit? This is how the board knows that those switches are closed. What is the operating command for this control board? Well, on a call for heat, it's 24 volts at W, so there's going to be a thermostat connected here. 24 volts is going to leave the control board, it's going to go through the thermostat, it's going to come back on the W. And that is then sensed also by the CPU. So when the CPU sees 24 volts on W, that is its trigger to say, do your heating thing, man. And now you need to know what that is. What is the sequence of operations? What is the sequence of operations of any gas furnace? Well, the first thing that happens on a call for heat is the draft inducer starts, right? That is one of the outputs. Where does that output come from? Here's our draft motor. And we can trace backwards. Here we are backwards. Comes from a Molex plug, PL2. And PL2 is on the going to be on the control board. Comes from AIDR, induced draft relay, on that control board. So check this out. Here is 24 volts at the L1 terminal, or I'm sorry, 120 volts at the L1 terminal. It goes on the board and it is sitting and waiting. 120 volts is our voltage pass-through supply, because on demand from 24 volts at W, draft inducer relay is going to close and send that waiting 120 volts to power up the draft inducer. Boom. After the draft inducer runs, the pressure switch is going to close. And here we have another voltage send and return binary digital input. It's receiving 24 volts on W, and that 24 volts now leaves the board through the Molex plug, passes through the pressure switch. Well, it just lands on the pressure switch and it waits. Once the draft inducer is running, then the pressure switch will close and allow that voltage to come back to the control board, and this is our voltage return. Then that voltage now becomes another pass-through while it sits and waits at the incoming side of the gas valve relay. Once the pressure switch is closed, the control board says, okay, man, time to go to the next step. What's next? Igniter has to glow. Where does the igniter get its voltage from? It comes through another relay that is in series with the draft inducer relay. So once the draft inducer relay closes, now we have a voltage supply for the hot surface igniter relay. When that relay closes, 120 volts comes out of the board and comes to the hot surface igniter. So in this case, if our hot surface igniter doesn't glow, is it possible that something in this circuit has physically broken or fails to operate even though it's supposed to? Absolutely. That would mean a bad control board. We have to replace the whole thing. So we want to look to see, hey, what is the job of this control board to do? It's actually to close these relay contacts, and that's it. It doesn't know if the igniter is connected. It doesn't know if it's glowing. It doesn't know any of those things. All it knows is that it's supposed to close these contacts. And when it does, 120 volts is going to leave on PL3, or I'm sorry, PL2, into PL5, out to PL3. Those are plug numbers, the Molex plugs that come apart. There's a couple of them on this one. Hey, could it be that one of these wires is broke? You betcha. So that's what's involved in the troubleshooting, is you have to understand exactly what this board is trying to do, identify how it's doing that, and identify whether or not it is doing that. And that takes a minute or two, right? It's not always immediately obvious, but that's what it takes. It takes a little bit of time. It requires you to take a look at the sequence of operations and identify what's going on. Fault codes. Just real quick, I want to reiterate that when you experience a fault code, sometimes there is helpful suggestions to tell you what to check for. Check this out for low heat pressure switch or relay did not close or reopen. There's a bunch of things it could be. And one of them, only one, is a defective pressure switch. There could be all kinds of other things going on there. So that brings us to our conclusion. And I want to reiterate that these are ideas that you want to think about while you're in your troubleshooting operation. Troubleshooting electronic circuit boards is not cut and dried. In fact, it can be very, very difficult. It can be very, very complicated. So remember to take this kind of step-by-step compartmentalized approach to it. Look at your power supply. Look at your inputs. Look at your outputs. What are you controlling? And is in fact that happening? And if it's not happening, let's identify exactly why. Try to take the mystery of your control board away and replace it with logic. And that's the hardest thing to do, especially when you're looking at something that you don't specifically know. Recognize, hey man, I don't know what this thing is supposed to do. I need more information, and get that information, absorb it, and then move on. All right, guys, thank you so much for your time and attention. Have yourself a great rest of your day, and I look forward to seeing you again real soon. Thanks.